Hello and welcome to our STEAM project number 18, featuring the Raspberry Pi Pico and MicroPython. This lesson is part of our Sherpa level series, designed for the somewhat experienced STEAM teacher. Today's project is going to optimize the yield of a solar panel in support of the Sustainable Development Goal 7, affordable and clean energy. We will program light-dependent resistors and a servo motor, all of this mounted on a cool 3D printed Tinkercad design. My name is Peter. I am the founder of Educomondo and a certified STEM instructor and course designer. The goal of today is to compare the input of two light-dependent resistors and apply that comparison to control the angle of a solar panel. And although we are using a miniature version of the solar panel, this is a real-life application with large solar panel farms. So first we will understand the basic working principle of a solar panel. Then we will monitor the continuous readings from the LDRs to control the servo motor. We will use a 3D printed Tinkercad design to mount the solar panel. And most importantly, we will make sure that you and your class works as a team to find solutions, help each other, and present their project in a clear way. Simply put, sunlight, in the form of photons, strike the silicon in a solar panel, causing electrons to move and create an electric current. This current is then collected and converted into usable electricity. It's a clean and efficient way to generate power from the sun. We will need the breadboard with a Raspberry Pi Pico and, of course, the pinout card, the solar panel, a servo motor, two LDRs, two resistors of 10,000 ohm, a bunch of jumper wires, and some form of support to mount the project. This is where you and your class engineering creativity comes in. This support can be made from cardboard, wood, or it can be a nice 3D project using Tinkercad. Students registered for this course can download the STL files created exclusively for this project. And here you can see the finished product. We assembled the frame to house the solar panel. The frame has 4 protruding arms where the LDRs will be put. They are slightly encapsulated in order to optimize the differences in LDR readings. The frame hinges between a U-shaped support, and the servo motor is screwed or glued to one pillar of the support. There are 4 spaces for the LDRs in case you want to experiment with the best position, or if you feel like adding another movement using, for instance, a stepper motor. Now it's time to go to our live Tony environment and do some coding. Welcome to our Thonny environment. As you can see, I have already prepared the program. So let's go through it line by line. Of course, we start with importing our modules and classes. And we also need to set up our servo motor as an object, and we do that on pin number 15 as a pulse width modulation. We have also seen in our previous lesson that we need to define the frequency, and that for this type of servo motor that we put it at 50. We have two light dependent resistors, a left one and a right one. The output that these resistors are going to give us are analog outputs, so we need to put them, or we need to link them to the ADC 26 or 27 pin on our Raspberry Pi Pico. Next, we are going to define a number of functions, and the first function is to map. You probably remember that we have seen this in the Arduino course, where C++ has an embedded map function. Python doesn't have that, but it's easy to create one yourself. So this is the syntax to be used in order to create your own map function. The next, what we want to do, the next step is to have another function where we are going to move the panel according to a particular angle. And the first thing that we want to ensure is that the servo motor is not going to overstep the predefined angle, which means that we don't want it to go beyond 180, 185, or below 0, let's say -5. We know that these servos are not exactly the most precise ones, so it's easily it can easily happen. In addition, when you run the project, you might decide that actually the angle should not go between 0 and 180, but for instance between 30 and 150, simply because otherwise it clashes with wires or for whatever reason. So this is also that you something that you can then change in this particular area. So we are already going to use our map number or map function in order to set the position, and the 4 numbers that we are going to use is the 0 degrees and the 180 degrees, and then the 1208 and 7864, which are numbers that are very familiar to you because we have defined those in our previous lesson as part of the duty cycle of the pulse width modulation. We want to control what this function is going to give us an output, and the easiest way is, as always, to print something into the RPI. And what are we going to print? Well, we're going to print the angle and saying what is the angle and what is the position of the servo that it relates to. The next function is where we are going to check and compare the output of the two light sensors. In this case, we work with 2 sensors. As we have seen, we actually have opportunity to include 4 sensors in this particular design, but we are only going to use 2. And we have a left and a right one. And of course, it's very easy to say or to compare this, the reading with the left read underscore U16. That's going to be the left variable, and the right variable is going to be the reading of the right LDR. We are also going to transfer that reading into a percentage because that's just a little bit easier for us humans to understand. So once again, we are going to call our map function, and we are going to map it between 0 and 6535, which is the theoretical range of an analog reading using the U16 method within our MicroPython, and we are going to map that to a percentage. A percentage, that's of course something that goes between 0 and 100. And we do that for both the left and the right. And once again, we want to check what's happening. So we want to print it as a line, and we're going to say the left brightness in percentage compared to the right brightness in a percentage. And the return is actually going to return a Boolean comparing the value of left with right, and when this is going to be true or false. And so this is a very concise way of comparing those two values and returning a Boolean, which, as you know, is either a true or a false. I think we are ready with defining our functions, and so we are ready to get into our continuous loop in our while true loop. But before we do that, it's maybe not a bad idea to move the panel to a certain angle, and I do that by just setting it for 5 seconds into the position of 90 degrees. Why am I doing it? Well, simply because that gives you the opportunity to, for a short period of time, to double check whether the panel is nicely horizontal, so that it is nicely calibrated, because, well, we've seen this is all plastic, so there might be some deviation after a while, that some of the screws or the connections come loose, and it may not really capture the mount of the solar panel correctly. So that will give you the opportunity to see whether everything is nicely calibrated from a mechanical point of view, really. And then we start with our while true, so our continuous loop. And we use a try except method, which is very common. So we will first of all check all the time which of the light sensors is the brighter, and we are using the left one as well. Use it as the comparator in order to make sure that we can always compare that with the other sensor. And we do that by creating a left is brighter variable, which is really something to check the light sensors, or is the output of the check light sensor. And we know that the check light sensor, the output is going to be this Boolean, so it's going to check it whether this is true or false. And if the left is brighter and the current angle is shorter or smaller, not shorter, but smaller than 180 degrees, what do? Well, we are going to move the current angle with a small position of 5, so with an increment of 5. And then what we say, well, we print, we move to the left because it's brighter over there. If it is not brighter and the current angle is larger than 0, then we are going to say, well, we are going to first of all do a decrement of 5, and then we say we are going to move to the right because it is brighter on the right side. And as an output, we move that panel to the current angle, and we stay there for 1 second. Now, only using 1 second will be pretty quick. So if you don't want this servo motor step-by-step small increments, you can play around with the duration of the delay here, so that you can actually ease out some of the mechanical movements. And we also have an exception. So if there is an exception as an error, then we are going to print, oops, something went wrong, and then we just stop for 5 seconds. so that you have some time to double check what's going on. And that can be any mistake here in this program. It's just going to give you a more user-friendly, although maybe not very precise, return and window of opportunity to correct the error message here. So that's the program. So let's give it a try and see if it works. So the first thing, it's going to convert the angle 90% to the servo position of indeed 4000 and so on. And now it's going to very, one by one, going to look for the brightest side from between the two sensors, the left or the right, which captures the most light, and then it's actually going into that direction. Once it had reached the 180%, it stops, and it will only go when it moves to the other side, when more light will fall on the LDR. And as you can see from the image here, it seems to be working quite well, following nicely the flashlights in order to mimic the sun, and it moves from left to right, or it moves from 0 to 180%, depending on the light source. I hope this also works for you. If not, well, you know it and your students know it. This is not the time to panic, but to conduct some critical review of the code and checking both error messages and the physical project. This project is a great starting point to talk about alternative energy sources. Let your students do research on SDG 7 and what it really means. They can do some research, for instance, on wind energy, hydrogen in all its various forms, hydropower, geothermal, batteries, nuclear fusion, and so on. Combined with the previous projects, you can now build a smart irrigation and water cycling project that is completely powered by solar energy. That's it for lesson 18. I'm confident that you and your class found it useful. In our next project, Project 19, we will take our first steps in the world of artificial intelligence and create an object recognition project based on the ESP32 CAM. And again, bye-bye for now.